we have some ML application, okay? So that is some needs, okay? Some needs. That means somebody have some requests. What are we going to do? Well, the first thing is we are going to turn this, so this is mathematics. We are turning this machine learning application needs into a what? Into a model, okay? Into a model, okay? So this is the first thing we need to do, number one. After we have this step one, what's the step two? Step two is how are we going to solve this model, okay? So we are going to solve this model by what? We're going to solve this model, okay? Solve this model, okay? Then we will get a solution, okay? So because this is a math model, the solution here is not necessarily the solution of this. So what we need to do after we solve this for example, we can call this algorithm, okay? We solve this, we get some solution. This solution is a solution for this model one. It's not necessarily the solution for the machine learning application. So after that, we will do something. This is called post-processing, okay? Post-processing. Then we will get something, okay? Let me call this, okay, let me just put a start here. We do some post-processing, then this will give us something. This one, supposedly, okay, supposedly, so I write ... solve this one, okay? And I put a question mark, okay? This is the idea. So the key idea in the whole thing is 1 and 2. Some people may say that, oh no, for machine learning, you need to do some data pre-processing so that you can go to 1. That's true, but I will put those within here. Okay, so this is more or less like the framework of machine learning. So I'm going to talk about 1 and 2, okay? So since we have some goal, okay, we have some goal in the machine learning application, so we want to write this goal, okay, we want to write this goal as a function f, okay? What is this function f? This function f can means a lot of things. For example, fx, let's say function fx, the closer to the 0, the better, okay? So, or the function fx, the closer to large value, the worse, okay? So what this f represents? This f represents cost, okay? In the mathematical optimization, they don't call this cost, they call it objective, okay? Just name, okay? Just name. So what is the goal? The goal is you have some machine learning goal, you write it down, so this is the step 1, modeling, as a function f. This f represents something. The bigger is this f, the worse is it. The smaller is this f, the better it is. So your goal is now converted to a function f. And what's your job here? The job here is minimize fx. So what is this thing? This means among all the x, so what is x? X is called decision variable, okay? Or we call it optimization variable, okay? So basically what is x? X is a variable. So you can think of x as a solution. So among all the possible way, find the x, the best x that minimize this. Why are we doing this? Because minimize this from here, it means smaller f, the better. And if the f is 0, let's say it's 0, then it solves this problem. So this is the whole thing. We want to find an x that makes this value as small as possible. So what's the meaning? So in a mathematical sense, x star, usually we write star to name this x is the optimum variable, is optimum. Okay, I just write opti, okay, or optimum, okay? For this, or minimizer this, if what? If what? F x star, what does it mean? The value of f at this point is smallest among all the fx. That means this thing is smaller or equal to fx for all x. That means among all possible x, this guy is smaller than every fx. Then of course this is smallest. This is exactly the meaning of smallest, okay? So we actually want to find this. This is the goal. You want to find the x star that is equal to the minimizer of this thing. That's the idea. Technically, this is wrong because this is a function value, this is an x, so it's not the same thing, but now we don't care, okay? So any question? No, then I move on. So basically the idea is you have some machine learning application, you convert them to a function f, and then you solve this thing, finding the best x that make this as small as possible. You may wonder, can we make this f as big as possible? Yes, if you want to make this f as big as possible, then this is not cost. This is called gain or benefit or yeah, whatever thing. So in that case, we want to maximize instead of minimize, but it's the same thing. So we don't care, okay? So now we will just look at this thing. So this is the idea. What are we going to do? We're going to minimize. This is minimize. We don't write the whole word. Minimize fx on x. This is a very general form, but usually we will have constraint. So we write s dot t dot. This means subject to, okay? Subject to, let's say x in C. What does C mean? C means constraint, okay? So that means you cannot have any C. The C need to fulfill some specific condition. Then this is a very general problem. So I just give you a very simple example. For example, okay, minimize x squared subject to x larger than equal 1. Suppose I have this. So how to solve this? You can draw a figure. So this is x. What is this? This is fx. What is x squared? X squared something like this. What is this? X larger than 1 is the same as x inside a set C. What is this set C? This set C is any x that x larger than 1. Right? What is this in the figure? It's like this is 1. Any x larger than 1, that means this region. So it's saying that I want to find the smallest value of this curve subject to x is within this region. Then it will be here, which is something like 1. So for this particular example, the optimum solution x will be 1 because it's here, and the optimum function value will be 1 squared, that is 1, which is here, 1. So for this particular problem, we know how to solve it. But in general, if I give you an arbitrary problem, nobody knows how to solve it. So therefore, in general, this kind of analysis is impossible. And we solve it by something called algorithm. So this is the idea. What I just showed you here is just an example that high school students know how to solve it. But now I'm talking about the general problem that nobody knows how to solve it. So that's the main thing. So how do we solve this thing? First, we were going to solve something like this. We will have starting point, okay, starting point x0. So this means iteration 0, okay? And then what you're going to do? You're going to do a for loop, okay? For loop for what? For k equal 1, 2, blah, 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 until let's say big K. So you're going to run k steps, 1, 2, 3, 4, 5 up to big K. And then what you're going to do? You're going to do is xk plus 1 equal to update xk. So what is this? This means starting from x0, at step 1, you have x0, you do update, it gives you x1. Then you do update on x1, it gives you x2. And then you do update on x2, it gives you x3, and so on. So you use the old one to get a new one. That is, this plus 1 basically means you get a new one. Then here's the question. What is this thing? This update has a function. You need to design this update such that this is true. That's the idea. So basically, how to solve an optimization problem? You design a thing called update. It can be anything. As long as fxk plus 1 smaller than fxk, if this is true, done. Why? Here's a simple explanation. Okay, I'm not trying to make this too mathematical, so something is wrong, but I just let you know. Suppose my function, my f looks like this, okay? And let's say I start x0 here. So my function at x0 is here. And let's say I do an update, and let's say the update is moving towards this place. And let's say the function looks like this, okay? Then the solution is here, okay? We know this is the solution. So suppose I have a point here, and then I get x1, and let's say the algorithm said move to here, and then I get this point. So this is my x1. This function value, that means the value on the y-axis, is lower than the previous point. This is true, so good. And then what? In the second step, the algorithm said that move from here to here, okay? This is x2, so now I have f here. This f value, the y-axis value, is lower than this x-axis, y-axis value. Function value go down. Good, so good. And then so on. I keep moving until what? You see, this is moving like this until I reach this point. And then when I reach this point, here's the thing. This is the condition, right? The condition saying that I want to make sure my function value in the next step is lower than the previous step. But don't forget there's an equal sign. So it's possible I have this. What does it mean? It means my function value doesn't move. From this figure, if my function value doesn't move, that means my x doesn't move. That means I finish. So this is the idea. So this means what? You want to design something called update that fulfill this condition. In general, this condition is not enough for the whole thing to work. But right now, for this simple example, this is enough to let you understand what's the meaning, okay? And here's the thing. How do you decide what update to do? This is a trial and error. You can say I run simple algorithm or I run very crazy algorithm, that's all fine. So the interesting part here is what is this thing for us to make this thing work? So this is the idea. Okay, so suppose I have a two-dimensional case. So R2, that means I have R times R, okay? So that means instead of X, I also have Y. And then the X here is a bunch of points in this coordinate space, okay? Then my function value fxy give me some number. It will be, let's say I call it Z coordinate. That means my plot will be 3D plot, okay? So for simplicity, let's say my fxy equal to x squared plus y squared. Then, okay, because of time, I'm not going to plot it, but I'm telling you what does it look like. It looks like something like this, a 3D cone, okay? Ice cream cone, okay? Something like this. What is the smallest value of x squared plus y squared? 0, 0, right? So in this case, the smallest xy should be 0, 0. You cannot think of other point that is smaller, right? Okay. Then, in this case, if I continue the previous illustration, let's say I start from here. Then, if you look from the top, you can imagine, let's say I'm here. Then, let's say 0, 0 is here. Okay, let's say 0, 0 is here. Then, from the top view, it means I want to move from here to here. Which means I want to move from here to here. So, in the algorithm, what does the algorithm say? The update has one condition. The update is fxk plus 1 smaller than fxk. So suppose I have a point, move to here, okay, move to here. If I look at the top view, let's say I move from here to here. Okay, then is this true? Yes, because for example, what's the value here? So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So at this point, this is 6, 4. Okay. Then the function value at this point it will be 4 squared plus 6 squared. Okay. And suppose now I move to here. The function value 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. So this is 4 and 2. So this is 4, 2. Then I will move my function value from 6 squared, 4 squared to 4 squared, 2 squared. Well, they both have 4 squared, I don't care, but 6 squared of course is bigger than 2 squared, so of course I make my function value go down. So that means if I move like this, it's good. Okay, this is true, so I can move like this. And then let's say in the second iteration I move to here. From 4, 2 to 1, 1. Then I move to 1 squared plus 1 squared. Of course this is bigger than this one. This is true. My new point is smaller than my previous point. This is true, then good. And then let's say in the next step it only moves to here. Okay, let's say it moves here. Okay, let's say it moves here, then what is it? 0.5 negative square plus 0.5. Okay. If this number is smaller than this number, this is okay. Because I only says I want the function value to go down. I didn't say my x cannot be negative. Okay? So it will be okay. Okay? Then let's say in the end it moves to here. Then equal to 0 square plus 0 square. Then this is of course smaller than this number. Then it's okay. And then after at 0 square, if I move to any arbitrary x square plus y square, here's the thing. You have no x, y that will make this function value smaller than 0 square plus 0 square. Then the algorithm should stuck at here forever. That means you finish. So this is the two-dimensional case. Now you have seen one-dimensional case and two-dimensional case. Then for n-dimensional case, it's the same thing. You have a bunch of x, x1, x2, x up to xn. For image, this can be pixel. For video, it can be photo. For sound, it can be audio. Then you want to find an f on this thing that this x makes this f as small as possible. What's the idea? If this is true, done. And of course, there are some conditions. Now I'm going to tell you what's the condition. For any f, it has to be, let's say, larger than 0 or larger than a number. Because if this number can go to negative infinity, then this will never end. Think about it. So let's say I have log x. What does log x look like? Log x looks like this. Then if I want to minimize this function, what's the minimum of this? It will be 0 because log 0 will go to infinity. But in computer, we cannot store infinity. So in the end, whenever you have a number that is very close to 0, you can always find another number that is smaller than your current number. That means your algorithm will never stop. So this is the problem. What we want is a function always go down, but it's always bounded by some number in the bottom, and this number is larger than negative infinity. Then this thing will work. Why? Because this is a very simple calculus argument. Okay, f is bounded below. Okay, and f is monotonically decreasing. Okay, something like this. Your step, make your function in your update, you make your new function value going down, smaller. Good. This is smaller than the previous step. This is smaller than the previous step. This is in the end smaller than the starting point. And this is true. And if all this thing, we have guaranteed fx for any x always larger than the number, it can be 0. As long as it's anything that's not negative infinity, then what you have? You are having something like this. You have a sequence that is going down. And all the sequences are always above a line called m. Then simple calculus tells you this thing converts to m. And since this is a smallest achievable value, that means you solve it. That means the two conditions you need in algorithm design. The first one is from the model. What's the model? Is that fx is larger than some small number, minimum. Okay, I call it m. Okay, and it can be equal. Equal means you reach the minimum. Okay, and this thing cannot be negative infinity, so this has to be larger than negative infinity. Okay, and the second thing is for the algo that on the update. Okay, you want to make sure that at the new point is smaller than the previous point. These two all together means your algorithm will work. Okay, eventually. After running 1 million iteration, 2,000 iteration, whatever iteration, eventually it will work. So this is the ultimate summary. So what you need is an algorithm that this is true, and what? Something like this is true, then done. Any question? The next thing will be, what's exactly the update? So as I told you, our goal is to what? Minimize fx on x subject to x fulfill some condition. Okay, now what we do, so the condition on the algorithm is that number one, f is larger than a number called minimum. This is not negative infinity, this is for all x. The second thing is, I want my new point smaller than my previous one. Then this is the condition. So what we can do is, xk plus 1, it can be what? Here's a very high level overview. Okay, you said I have a previous point, this is my new point. I move along my current point direction. This is my direction. So this is like how I move, okay? And then I multiply how big it moves, so I call it alpha k. Okay, some people write this as d. D means direction. That's totally fine, but I don't write d because you are going to write df dx, then the df dx in the calculus will confuse with the d here, so I don't write it. So I write delta. So it's delta. Delta is the direction, okay? What is this? It's called step size, okay? In machine learning, people call it learning rate, okay? I don't like this word because now we are doing optimization. There's nothing called learning here, so this is just sometimes people mix up. Okay, anyway. Then what are we going to do? We have a point. We move along a direction. This is something from the algorithm, and this is a step size. This can be something from the algorithm, or this can be something from you. So let's say you are lazy. You just said, I put all alpha equal to 1. That means every time I only move 1 unit. That's fine. If this two condition is true for this, then it's okay, right? But in some case, if 1 make this works, can we make this number bigger? That means we move longer. Maybe moving longer step will make this whole thing run faster. Who knows? Nobody knows. So therefore, this number, step size, lazy people just use 1 or use a constant, but maybe you change this number due to some update rule. That means there's an update rule inside this alpha. It's all totally possible. So we are not going to talk about this detail yet. We are going to talk about what is this. The simplest thing of this is negative of the gradient of f at the current point. So what the heck is this thing? So let me explain. So first, let's say my f has 3 variables. So fx is a function of x1, x2, x3. What is this? This thing, this symbol represents partial derivative f x1, partial derivative f x2, partial derivative f x3. It means I take derivative of this function f only seeing the first x1 as a variable, other thing I see a constant. This means I take derivative of this guy, but I only care about the second variable. 1 and 3 for me is constant. And if this, I only see the x3, other guy are constant. So let's give an example. So the example, let's say fx is x1 squared plus x2 squared plus x3 squared. Then what will be this? This will be partial derivative x1, the whole thing I copy. This is f, right? So I copy everything here. x1 squared plus x2 squared plus x3 squared. This is partial derivative on x1, so I don't care other guy. And then now the second guy, I copy everything here. So x1 squared plus x2 squared plus x3 squared. This is partial derivative on x2 squared, so I don't care about the first guy. I don't care about the third guy. And lastly, copy here, it will be, okay? Then here's the high school calculus, okay? What is dx squared dx 2x, right? So therefore, this guy give me 2x1, this guy give me 2x2, this guy give me 2x3, or I can write 2x1, x2, x3, which is 2x. Okay? So therefore, if I have this, then my gradient will be 2x, or 2x1, x2, x3. So this is an example. This is a very simple example. So let's say I have fx is, okay, x1, x2, x1, x3, x2, x3. Something like this, then what will be this? Okay? It will be, okay, partial f, partial x1, partial f, partial x2, partial f, partial x3. So I copy everything here. I only care about x1, so this one have no x1, I don't care, so it will be x1, x2, x1, x3. This one is on x2 only. This has x2, this has x2, no x2, I don't care, so x1, x2, x2, x3. This is on x3, so this one and this one, okay, x1, x3, x2, x3. So now do calculus. This is on x1, so x2 is constant, x2, this is constant, x3. So what is this? x1, x3. This will be x1, x2, okay? Okay, so this will be my gradient. And then, here's the thing. In the end, this can be any function. If I put a square root here, if I put a log here, if I put a square here, the same, okay? And you just do the thing. In machine learning, let me tell you, nobody will use this for modeling the machine learning application. So don't worry about seeing crazy function. No, okay? Most of the time, we will see is just square or square root. Yeah. So therefore, this guy is just negative of gradient, okay? And you know how to do this for many functions. What are the crazy functions? Okay, you won't see this. You won't see, let's say I have the same thing. You won't see cosine x1, x2e, and then x2, x3, log x1, and then square root x3. No, you won't see this kind of thing. This is like the calculus in year 1 for making your brain sucks, okay? But in machine learning, first of all, as I said, we have a machine learning goal to solve some problems, and then we model a function f that solves that machine learning problem. If this function appear in our f, that means your machine learning problem probably is some crazy shit that you need this kind of thing. That means very high chance you make a wrong f. Okay? Most of the time, f is structure. That means it is some fundamental function. You won't see this kind of thing. Okay? So don't worry. Okay? So we have this. Then what is this whole thing? This whole thing has a name. Hk minus, and then I put the alpha in front. This thing has a name. This thing is called gradient descent. Okay, so what does it mean? You have a function, you have a point. What's the slope? The slope here is positive, so you make it negative. The slope here is a number in the x direction. The slope here is a positive number. You make it negative, so you point in this direction. Multiply how much you move in the x, so this is like how much is the alpha. Then you move from this point to this point. You move from this point to this point. And then the slope here is slightly larger than 0, but you make it negative, so you move in this direction, and then you move certain amount of alpha, then you move here. So you see, it's slowing down. So this is like the most natural algorithm. You move along the negative direction of the slope, and then you multiply the step size. For laziness, you just say this is 1. Then you basically just move backward, and then you reach here. What about if your function, you are at here? Then the slope here is negative. Negative of a negative means positive. That means you move here. And then you move alpha amount. So you move from here, alpha amount to this point. The y value will be here. This value is lower than this value. Then yeah, okay. Okay? What happens if you are reaching the solution? If you reach the solution, well, recall from calculus. When you reach the extremal point of a function, gradient is 0. So when you reach this point, this guy is 0. This guy is 0. I don't care what is this value. So this whole thing is 0. New point is 0 point. Doesn't move. You solve the problem. You see? So this is a very basic algorithm. So basically, let me recap. So you are having an algorithm that is new point is 0 point plus a moving direction. What I just said is the moving direction is negative gradient, but you can do something else, right? Okay, times the step size. So I just show you that this guy can be negative gradient. Okay, but you can say I don't want to do negative gradient. I do something else. You can, but not the focus today. Okay. In fact, I will talk about what are the other possible choices. The other possible choice is I just show you. Okay, not today. This guy, the other possible choice is gradient multiplied by the second order derivative. This is a matrix. You take the inverse. This can be another delta. Okay, I forgot negative. Okay, this can be another delta. This is actually called Newton's direction. Okay, this is somehow invented by Newton. Okay, the difference here is that you can think of this thing is a second order derivative, and if you remember calculus or second order derivative, it's like the rate of change of slope. So this somehow tell you the curvature of the thing, and you are using the curvature to correct your direction. Somehow it will make this faster, but not the focus now. This because this thing is complicated. Not today. Okay, not today. So this is the idea. So you do gradient or you do algorithm such that this is true. And if this is true, together with 1, as I said, you keep going down and your function is bounded below. So in the end, it will converge. So that's how we solve a problem. And this is so powerful that it can solve any f. Because if you look at here, did I say anything on f? No, I didn't say anything on f. It can be any f. I only say that f need to be bounded below. I have an image. Okay, I have an image here. This is my image. So this, let's say this is my x bar. And then what I do, I have a camera. Okay, I have a camera. Okay. Take photo of this image, and then what? Somehow the person taking photo is shaking. Okay, then you get some blur. Okay, you get some blur. So how do I draw blur? Let's say you have motion blur. Okay, and then the image is not clean. Okay, so the machine learning problem can be: I give you this, please give me this. So you need to design what? You design a function f, minimize this function f, will remove the blur, then it will give you back this. So this is like an example. Okay, then of course the question is what kind of function describe blur? Then this is domain knowledge, expertise. That means we need to look at what is the function that describes blur. If I said we want to do this thing, so what will be? It will be ax minus b, something like this. Okay, what is this? This thing is my x. Okay, this thing is my b. This process taking a photo, I call it a. So it's like a multiply x give me b. So I'm saying a multiply x give me b. Now I'm saying that I have blur right here. Then ax minus b means it's the same as e error. I want to make the error small. Then I will get this back. When you can think of the error, it's like the error is not the posture, not the person. Error is basically like this or this kind of thing. Okay, you want to remove this kind of thing, then subtract this from this, give you back this. That means you want this to be small. That's the idea. So therefore, in this setting, what is the f? The f will be minimize ax smaller than b. Okay, this is a vector because this is a bunch of numbers, so this is a vector. So you need to have some function, right? Let's say we use 2 norm. So what's 2 norm? It's just x1 squared plus x2 squared plus, right? Okay, then you want to minimize this. And actually this is same as solving linear system ax equal b, but we now consider optimization. Okay, then minimize, okay, ax minus b 2 norm squared. Okay, so what is this? This is the same as minimize what? Summation. Ax means what? The row of A multiplied column x. So I will write aix minus b. Okay, let me draw a figure. You have A, you have x minus b. So this is same as this row A1 dot product with the whole x minus b1. So this is the first guy. And then you have this row dot this minus this. So it will be something like this, right? Then this is the this is called squares. Okay, you want to minimize this. Then what you do? Well, I call this f. This is my f. Okay, this is my f. What I do? Xk plus 1 equal xk minus step size gradient. Then I need to do this. Then that means I need to do this. So what I'm going to do this. What is this? It will be partial derivative x1 and so on, right? Then let's look at what is the partial derivative of the first guy. The partial derivative of first guy will be partial derivative first guy of this whole thing. This whole thing. Okay. Aix minus b squared I. Okay. Only on x1. This one, what is this thing? So my partial derivative f x1 will be partial derivative x1 what? This row dot this guy minus b1, so a1 x minus b1, and then this row dot x minus b2 plus a2 dot x minus b2, of course there's a square, and then blah blah blah. So I have a bunch of points, and you know I can just take derivative on each of them, take the sum. Then that means I need to think about how do I solve this thing. What is this? This is the same as gradient of what? Phi inner product x minus c squared. Okay, then chain rule, okay, or product rule. Okay, something like this, right? Just put the 2 here, the thing here, and then d the thing inside. So you have this. This is constant, so I don't care. This is what? This is derivative of the inner product. Okay, I keep the time. It will be just this guy. Okay, it will be just this guy. So therefore, this term, the detail I will talk about next week or later, but I just skip the detail. So this guy will be what? 2 come out, the whole bracket. Okay, I just write the bracket. The a vector here. This guy will be 2 come out, the bracket here, a2 bracket here. So therefore, this will be what? This will be the derivative of the first term. And then the only changes for the second term is only the thing inside the bracket. Everything the same. So now I skip the detail. Okay. This thing, I skip the detail. If you rearrange everything, it will look like A transpose AX minus A transpose B2. So this is the gradient. Here, let me make it clear. The derivation of this to here is not the focus. If you don't know how to do that, doesn't matter. There will be table. You just look at the table and then you see what table you can use. This is totally not a problem. Okay, so you move from here to here, then what you do? This, right? So therefore, your update operation will be alpha is a number. So let's say I have alpha. Gradient, that is 2. Okay, now let's say I absorb the 2 into alpha. That means I make alpha half. Then I don't need to write the 2. This thing. Now you see there's x. This is what? xk, right? This thing is what? Alpha A transpose A xk, right? Minus and minus give you positive. Okay, these two I can combine, so I have I minus alpha A transpose A whole thing x plus alpha A transpose B. A, B are given, is a constant, so I just write it as alpha C x k plus 1. This thing, if alpha is a constant, then this thing is just a constant matrix. So therefore, the update will look like something like the xk plus 1 equal to a matrix multiply your previous point plus a constant. And you keep running this. So this basically will solve this problem. And what is the physical meaning of this? You can think of this M matrix as a, matrix. What is matrix? Multiply matrix means you rotate a vector, scale a vector, or enlarge a vector, right? So this M, if you multiply this M like this several times with a good alpha, this is saying that you rotate your x, enlarge your x to make this guy small. Then, if you run this long enough, this xk will reach the solution of this thing. That means you will reach an x that ax equal b. Okay, so let's say if there's no error. But if there's error, you will reach an x such that the error is the smallest. Okay? Error is the smallest means this is the part of the E cannot explain by the A. Because as I said, you take a photo of a person using a camera, okay, and then you get the photo with blur, okay, and if this camera is like a matrix A, that means it represents the optical characteristic of the system. Blur is from you, is from the human, does not matter from the camera, so the camera cannot know how much you move your hand or shake your hand. So the E, that means the blur here, shouldn't be captured by the camera. So if you minimize this error, it should give you the blur. The math detail is not important because I didn't talk about too much detail. For example, what is the alpha? I just let you know what is the alpha here. The alpha here, people say just guess. No, actually the alpha here will be the A transpose A 2 norm 1 over. This is a good choice. You may ask why, not this time. So basically, if you run this thing, this is the gradient. You find this gradient by calculus or look at the table from a book, then you find this thing. Alpha is a step size. You either tune it or you use formula. Now I'm giving you a formula that is 1 over A transpose A2 or 1 over the singular value of A, largest singular value of A, or the largest eigenvalue of A transpose A. Okay, these are formula next time. Then you run it many times, it will solve this problem magically. Okay, so this is the overview. I'm not saying you need to remember all the math. You need to know the idea, not the math. Math is just, you should work on the math on your problem, not this problem. Okay, if you work on this problem, then you need to know the math here. But if you don't work on this problem, it doesn't matter. Then now I have this thing. X larger than 0 means everything inside is larger than 0, cannot be negative. Then in this case, I have this thing. Then here's the thing. If I have this constraint, okay, this is the general step, right? I have a direction, I have a step size, I move my new O point to a new point. The picture is like this. I have a step C, I have a point here, X here. Here's the thing. This direction is possible. These two guys work together, will move the point to here. But I said I want the X to be inside set C. So if I move the point to here, what does it mean? It means the X is not in C. That means wrong. Because I said I want X to be in C. It can be something like this. For example, let's say X represents energy. This is some electric motor or some mechanical system. I want to find the minimum energy required to run some system. Energy is positive, so you cannot have energy negative, right? So you need to fulfill this. Then this approach doesn't work. You have two ways to fix this. Number one is do not move this point outside the set C. So you make this alpha smaller by just go to here. Or this is the first thing. The second thing is after you go outside set C, you go back. You come back. So how do you do that? Let's say this is C. Let's say your point here. I have a point. After I do this, what I do? After I get this point, I go back to the set by finding the closest point in this set to this point. What does it mean? Imagine I have a circle here. What does this circle mean? Circle means every point on this circumference have equal distance to this point, right? It's a radius r. So basically, I'm growing a bunch of circles until I touch this C. Then this point will be the X I have to project. So this is the idea. Again, I'm not talking about the math in detail, but this is just an overview. So what you are going to do is, you have a C, you have a point here. Here's the idea. You find the tangent, you know tangent, right? That means 90 degrees to this point. Then this point coming back to here will be in C because you want to have X in C. This approach is different from this approach. This approach is I change this alpha to smaller value such that when I move along this direction, I didn't go outside the set. This is after I do this thing, I go back. So this corresponds to this, and this one is xk plus 1 projection onto C, and I do the old stuff. So this PC means project back to C. This PC means project. And there's a math formula for you to do that. And there's some example. For example, if I projection to larger than 0, what's the projection? Projection to larger than 0 is just max 0. Why? Suppose x is negative 3. What's the closest value to the positive number? 0, right? So if x is negative 3, projection to positive, you just make it 0. And if x is 3, 3 is already inside C, so I do nothing. So if I have 3, output should be 3. So 3 and 0, what's the largest value? 3. So this is the answer. And what happens if x is 0? Well, 0 is larger than 0, right? So I can shift 0. Or 0 and 0 max itself is also 0, so it's correct. And then what about let's say I have a 3x plus 2y equal 1. I have a point 4, 2. I want to project onto this. Then you find the normal of this vector, and then you find the linear algebra projection onto a normal plane. This will be year 1 linear algebra thing. There will be a formula. And again, I don't remember the formula. Don't worry, we will look at the table, okay, or textbook. It will probably be some A transpose X minus something A divided by norm A something. I forgot the detail, but something like this. Okay, the A here will be the normal. That means 3, 2. Okay, I don't remember either. Or same thing, you have a matrix X. Now I have a set C. This is a funny set. That set C is all the matrix Z such that the largest eigenvalue of Z is 1. Project this to this. There will be some formula. We don't know. I don't know. You can do that. Or you can say that I have a variable X. This X is like a time series or a time sequence. And I'm saying that the C is all the X that is smooth. What does it mean smooth? That means this thing is impossible because this is a big jump. Smooth means something like this. Okay. That means what? If I project this to this, there will be a C telling you this is not okay, this is okay. Then you will have a C and you will find the expression of this PC. Then it will change from this to this. This will be useful. So the summary is like this. You have a machine learning problem, MLQ. You write it as a F, minimize a F. This is called modeling. Okay. And then you have this thing you want to solve. So you do something called algo. Now you know what's algo is update. What is update? New point equal to update old point. And this update can be xk plus direction times step size. And then you get your solution x star. Why this is true? Because you assume f new is smaller than the previous f, and all the f is larger than something that is not negative infinity. And this too is true with the update rule. You will always converge just 1 hour or 1 week, because some problem takes 1 hour to run. Some problem takes 1 month to run. Deep learning takes 1 year to run. Okay. Then after you get this, you go back to here, do some post-processing, see whether or not this is the solution, and that's it. And the detail here inside is just derivative. That means multivariable calculus, okay? And this is, we are not studying how to do calculus. So for those calculus you don't know how to solve, doesn't matter. You look at the book, there are some table, formula, or you ask me, okay? So the funny thing is, how to do part 1 and how to do part 2, okay? This is not, okay? The research basically how to do part 1, how to do part 2. And of course, what does it mean? How to do part 1, how to do part 2 means you write down on paper part 1 and part 2, and then convert them to program, and you run it. Because this thing you are going to run 1 million iteration, you cannot run by hand. You have to run use a computer. So that's the idea. These are like the overview. Any question? No? Good. Then see you next week.